This is section 4.2 of our textbook. This section covers linear combinations. Before we get started, I'll just ask you to bear with me here. This is my first time trying to deliver a lecture in this format, so it might be a little choppy. But the big idea here is, if you recall last time in lecture, we saw that a vector space is more general than what we might just consider from what we've seen in the past with Rn or Cn vector space. We did see when we talked about vector spaces Rn and Cn that this idea of linear combination is actually a crucial concept, and so we want to see how to consider this in the more general vector spaces, not just Cn and Rn here. So let's take a look here, starting with the definition that should look very familiar to us. If we let v1 through vm be vectors in vector space V, then the vector v in that vector space is a linear combination of vectors v1, v2, all the way through vm. If there exist scalars c1, c2, all the way through cm, such that the vector v we started with is c1 times v1 plus c2 times v2, all the way up to cm times vm. So we're just saying if we can write this original vector as some part v1, some amount of v1 plus some amount of v2, all the way up to some amount of vm, then we are able to say that v is a linear combination of these vectors v1 through vm. And so we'll see that once we get into this, it becomes obvious that in general, determining whether one vector is a linear combination of other vectors really typically involves solving a linear system for these scalars c1 through cm. And so let's see that with an example just in R3, something we're a little more familiar with to get started. So in this example, we're asking, is the vector -2, 11, 7 a linear combination of 1, -1, 0, 2, 1, 4, -2, 4, 1? Like I said, these are vectors in R3, something we're pretty familiar with here, so this probably won't seem too strange. But let's jump in here and see how we would handle this problem. First, I'm going to say that this vector we're starting with, in order to be a linear combination of these three, we better be able to write this vector -2, 11, 7 in the form -2, 11, 7 equals c1 times 1, -1, 0 plus c2 times 2, 1, 4 plus c3 times that last vector, -2, 4, 1. And if we can solve this system for those c values, c1, c2, c3, we will know that, yeah, -2, 11, 7 is a linear combination of those other three vectors. So we try to solve this this equation for c1, c2, and c3. But if we're careful here, all we're really looking at is a vector on the left equals a sum of vectors on the right, and the sum of vectors is just a vector itself. Well, to get the left side vector equal to the right side vector, we just need each corresponding component to be equal. So we can actually break this vector equation into really three different scalar equations in this case. Let's see what those are. Equating the first components on left and right side of the equation will tell us that -2 from the left side equals c1 times 1 plus c2 times 2 plus c3 times -2. I'll just write it that as -2 c3. Equating second components, very similar. You get 11 is -c1 plus c2 plus c3. And finally with last components, we get 7 is 0 here, won't even write it, plus 4c2 plus c3. And so we notice that at the end of the day, this problem reduces down to just solving a linear system here. A linear system here for those scalars C1 through C3. And so to solve that, I'm actually just going to pack this up into an augmented matrix, the coefficient matrix here, and the constant column augmented to the end of that. Let's fill this out. Put a 0 there. And so we get this augmented matrix. Right. And as you know, to solve a system using an augmented matrix, we typically just take this augmented matrix and we reduce it down with row operations as far as we need to so that we can unpack it and solve the system easily. So from here, I'll just skip all the details, leave that to you to check. But when I do this reduction, I get the matrix reduces to 1, 0, 0, 2, 0, 1, 0, 1, 0, 0, 1, 3. And of course, that's trivial to unpack or to get a solution from. We just write down C1 equals 2, C2 equals 1, and C3 equals 3. So that means, yeah, we were able to solve this equation for C1, C2, and C3, meaning, yeah, we can write this original vector, negative 2, 11, 7. We can write it as C1 was 2, so we can say this is 2 copies of 1, negative 1, 0. C2 was 1, so we'll add 1 copy of 2, 1, 4. And C3 is 3, so we'll add 3 copies of negative 2, 4, 1. And what we have here is really, well, I guess all this, is the negative 2, 11, 7 vector written as a linear combination of the original set of vectors. 1, negative 1, 0, 2, 1, 4, and negative 2, 4, 1. And that is the general procedure. If we want to take a given vector like negative 2, 11, 7 and see if it is a linear combination of 3 other given vectors, we're just trying to solve this system, which amounts to a linear system that we already know the procedure for. If we can solve it, which we could in this case, then we can say definitively, yeah, that vector we started with is a linear combination of the 3 given vectors. We'll continue in the next video.